Einstein's early curiosity and non-traditional education played a decisive role in shaping the revolutionary thinker he later became. Unlike the popular myth of Einstein as a flawless genius from childhood, his early years were marked by questioning, struggle, and a deep resistance to rigid systems of learning. These experiences did not hinder him. Instead, they nurtured the independent mindset that allowed him to transform modern science. Albert Einstein was born in 179 in Ulm, Germany, into a middle-class Jewish family. His father and uncle ran an electrical engineering business, which exposed young Albert to scientific instruments and technical discussions at an early age. One of the most famous moments of his childhood occurred when he was around 5 years old and was shown a simple magnetic compass by his father. The invisible force that caused the needle to move fascinated him deeply. He could not see or touch what made it work, yet it clearly obeyed some hidden law of nature. This moment planted a powerful idea in his mind. There were unseen forces governing the world, and understanding them was both possible and meaningful. This sense of wonder never left him and became the foundation of his scientific curiosity. Despite his curiosity, Einstein did not thrive in traditional classrooms. He attended a rigid German school system that emphasized discipline, memorization, and obedience to authority. Teachers expected students to accept information without questioning it, an approach that clashed directly with Einstein's nature. He disliked rote learning and felt constrained by strict rules and military-style discipline. Rather than excelling through memorization, he preferred to understand concepts deeply, asking why, instead of simply accepting what. This attitude often brought him into conflict with teachers, some of whom viewed him as slow, rebellious, or lacking promise. One common myth is that Einstein failed mathematics as a child. In reality, he excelled in mathematics, mastering advanced topics such as calculus at a very young age. However, his brilliance did not always translate into high praise because he refused to conform. He was more interested in exploring ideas independently than in performing well on standardized tests. His true education often happened outside the classroom through study and curiosity-driven learning. At home, Einstein found freedom to explore knowledge in ways that school did not allow. He taught himself geometry and algebra by working through textbooks on his own, often discovering results independently before learning they were already known. He also read popular science books that explained physics in imaginative and accessible ways. These books encouraged him to visualize physical phenomena rather than merely calculate them, an approach that later became central to his scientific method. Einstein relied heavily on thought experiments, imagining scenarios in his mind to test ideas, which became one of his most powerful tools. Einstein's non-traditional education became even more pronounced during his teenage years. When his family moved to Italy for business reasons, Einstein remained in Germany to complete school. He quickly became unhappy and eventually left the school without finishing his formal secondary education. This decision reflected his growing rejection of authoritarian instruction and his desire for intellectual freedom. Later, he enrolled in a Swiss school in Aarau, which followed a far more progressive educational philosophy. This environment emphasized creativity, independent thinking, and discussion rather than strict discipline. For the first time, Einstein felt intellectually at home. The Swiss school had a profound impact on his development. Teachers encouraged students to think critically, question assumptions, and explore ideas openly. Here, Einstein began imagining scenarios that would later form the basis of his theories of relativity. One such thought involved chasing a beam of light and wondering what it would look like if one could travel alongside it. These imaginative exercises were not part of any formal curriculum, but they were central to his learning. This period demonstrated that Einstein flourished when given intellectual freedom rather than rigid structure. After finishing school in Switzerland, Einstein entered the Swiss Federal Polytechnic in Zurich to train as a teacher of mathematics and physics. Even there, his non-traditional approach continued. He often skipped lectures, preferring to study on his own or discuss ideas with friends. Instead of relying on professors' notes, he focused on original papers by leading physicists and developed his own understanding of fundamental problems. While this independence strengthened his thinking, it also led to academic difficulties. Some professors were unimpressed by his lack of conformity, which later affected his chances of securing a university position. Einstein's struggles within formal academia highlight an important aspect of his education. It was largely self-directed. He learned not because he was told to, but because he wanted to understand the universe. This intrinsic motivation made his learning deeper and more durable than conventional instruction. His curiosity was not limited to physics. He also explored philosophy, reading thinkers such as Kant and Hume, which influenced how he thought about space, time, and knowledge itself. Perhaps most importantly, Einstein's early experiences taught him to trust his own reasoning. Because he was often misunderstood or undervalued by teachers, he learned to rely on internal logic rather than external approval. This independence was crucial when he later challenged established scientific beliefs. Proposing that time could slow down or that gravity was the curvature of spacetime required immense confidence in one's own thinking, especially when confronting centuries of accepted wisdom. In summary, Einstein's early curiosity and non-traditional education were not obstacles but essential ingredients in his development as a revolutionary scientist. His wonder at invisible forces, resistance to rigid schooling, passion for self-learning, and exposure to progressive educational environments shaped a mind capable of questioning the deepest assumptions about reality. Rather than being molded by traditional education, Einstein reshaped education's purpose itself, proving that true understanding comes not from memorization or obedience, but from curiosity, imagination, and the courage to think differently. The year 1905 is remembered as Albert Einstein's miracle year, a period of astonishing intellectual productivity that permanently transformed physics. In a single year, while working not as a university professor but as a modest patent clerk in Bern, Switzerland, Einstein published a series of papers that challenged the foundations of classical science and opened entirely new directions of thought. These breakthroughs reshaped humanity's understanding of light, matter, space, time, and energy, and established Einstein as one of the greatest scientific minds in history. At the start of 1905, Einstein was largely unknown in the academic world. He held no prestigious position and worked long hours reviewing patent applications for electromechanical devices. Yet this job, surprisingly, gave him mental freedom. Away from academic pressures and expectations, Einstein had the time and independence to think deeply about fundamental problems. Physics at the time was facing serious contradictions. Newton's laws worked well for everyday motion, but they struggled to explain behavior at very high speeds or very small scales. Experiments involving light, heat, and atoms were producing results that classical theories could not fully explain. Einstein entered this scientific crisis with a fresh perspective, unburdened by tradition. one of Einstein's most important breakthroughs in 1905, addressed the nature of light itself. For centuries, light had been understood mainly as a wave, a view supported by many successful experiments. However, certain observations, such as the photoelectric effect, did not fit this model. When light shone on a metal surface, electrons were ejected, but only if the light had a certain minimum frequency. Increasing brightness alone did not help, which contradicted wave theory. Einstein proposed a radical idea. Light is made of discrete packets of energy, later called photons. Each photon carried energy proportional to its frequency. This explanation perfectly matched experimental results and laid the foundation for quantum theory. Although controversial at the time, this insight later earned Einstein the Nobel Prize in Physics and became essential for modern technologies like solar cells and digital sensors. In another 1905 paper, Einstein tackled the puzzling issue of Brownian motion, the random movement of tiny particles suspended in a liquid. Observed decades earlier, this motion had remained unexplained. Some scientists even doubted the existence of atoms, considering them merely theoretical constructs. Einstein showed that Brownian motion could be explained by countless collisions between visible particles and invisible atoms or molecules in the liquid. By mathematically describing this motion, he provided strong evidence that atoms were real physical entities. This work played a crucial role in convincing the scientific community of the atomic nature of matter and strengthened the foundation of modern chemistry and physics. Perhaps the most famous achievement of 1905 was Einstein's theory of special relativity. At the time, scientists believed that space and time were absolute, fixed backgrounds against which all motion occurred. However, experiments involving the speed of light suggested contradictions. Light appeared to travel at the same speed regardless of the motion of the observer, a result that could not be explained by classical mechanics. Einstein approached the problem by questioning basic assumptions rather than adding complex fixes. He proposed two simple principles. The laws of physics are the same for all observers moving at constant speeds, and the speed of light in a vacuum is the same for all such observers. From these principles followed astonishing consequences. Time was no longer universal. It could pass at different rates depending on motion. Lengths could contract, and simultaneity itself became relative. Events that appeared simultaneous to one observer might not be so to another. These ideas were deeply counterintuitive, yet they were mathematically consistent and experimentally verifiable. Special relativity redefined the concepts of space and time, merging them into a single framework that would later evolve into spacetime. Closely connected to special relativity was another groundbreaking result presented later in 1905, the equivalence of mass and energy. In a short but profound paper, Einstein derived the now famous equation E equals mc2. This simple formula revealed that mass is a concentrated form of energy, and that even a small amount of mass contains an enormous amount of energy. This insight transformed physics and had far-reaching consequences. It explained how stars produce energy, laid the groundwork for nuclear power, and influenced the development of modern particle physics. Though Einstein himself was uneasy about some later applications of this idea, its scientific importance cannot be overstated. What makes the miracle year truly extraordinary is not only the number of breakthroughs but their depth and independence. Each paper addressed a different fundamental problem, and each one alone would have secured Einstein a place in scientific history. Together, They revolutionized multiple areas of physics at once. Even more remarkable is that Einstein achieved all this without the support of a major laboratory or academic institution. His work demonstrated the power of imagination, logical reasoning, and a willingness to challenge deeply held assumptions. Initially, Einstein's ideas were met with skepticism and resistance. Many physicists struggled to accept the notion that light could behave like particles, or that time itself was relative. However, as experimental evidence accumulated, his theories gained acceptance. Over time, the insights of 1905 became cornerstones of modern science, influencing everything from quantum mechanics and cosmology to everyday technologies like GPS systems. In essence, the miracle year of 1905 marked a turning point in human understanding of the universe. Einstein did not merely solve existing problems. He transformed the questions scientists asked and the frameworks they used to seek answers. His breakthroughs revealed a universe far stranger and more beautiful than previously imagined, where light comes in quanta, atoms dance invisibly, time bends with motion, and mass itself is a form of energy. The legacy of that remarkable year continues to shape science and technology, reminding us that revolutionary ideas can emerge from the most unexpected places when curiosity and imagination are allowed to roam freely. Special and general relativity are two of Albert Einstein's most important ideas, and although they are famous for being complex, their core ideas can be explained in a simple and intuitive way. At their heart, both theories are about how space, time, motion, and gravity really work, not as we imagine them in everyday life, but as they truly behave in the universe. Special relativity, introduced in 1905, begins with a simple but shocking idea. The laws of physics are the same for everyone who is moving at a constant speed, and the speed of light is always the same no matter how fast the observer is moving. This goes against common sense. In daily life, speeds usually add together. If you throw a ball from a moving car, someone standing still sees the ball move faster than the car itself. But light does not behave this way. Whether you are standing still, moving slowly, or traveling extremely fast, you always measure light traveling at the same speed. To make this work, nature makes a trade-off. If the speed of light is fixed, then space and time cannot be fixed. Time must slow down and distances must shrink for objects that move very fast. This is not an illusion or a trick of measurement. It's maturity. A clock moving at high speed ticks more slowly than a clock at rest. This effect, known as time dilation, has been measured many times using precise atomic clocks on airplanes and satellites. The faster something moves, the slower its time passes compared to something at rest. At the same time, objects moving at high speed become shorter in the direction of motion. This is called length contraction. To the object itself, nothing seems strange. The traveler does not feel time slowing or their body shrinking. These effects only appear when comparing one observer's measurements to another's. This leads to one of the most surprising ideas of special relativity. There is no single, universal now. Two events that seem to happen at the same time for one observer may happen at different times for another observer moving at a different speed. Time itself depends on motion. Special relativity also reveals that mass and energy are deeply connected. Einstein showed that mass is a form of stored energy, expressed in the equation E equals mc2. This means that even an object at rest contains enormous energy simply because it has mass. This idea explains how stars shine, how nuclear reactions work, and why small amounts of matter can release huge amounts of energy. Special relativity applies only to situations where motion is constant and gravity is not involved, but it completely changed how scientists understood space and time. 10 years later, Einstein went even further with general relativity. While special relativity deals with motion, general relativity deals with gravity. Before Einstein, gravity was described by Isaac Newton as a force that pulls objects toward each other. This explanation worked extremely well for centuries, but Einstein realized it was incomplete. He proposed a far more radical idea. Gravity is not a force at all. Instead, gravity is the result of the bending of space and time caused by mass and energy. To understand this, imagine space and time as a flexible fabric called spacetime. When an object with mass, like the Sun or Earth, exists in spacetime, it causes this fabric to curve. Smaller objects then move along these curves. From our perspective, it looks like gravity is pulling them, but in reality, they are simply following the natural shape of spacetime. A helpful analogy is placing a heavy ball on a stretched rubber sheet. The sheet curves and smaller balls roll toward the heavy one, not because they are pulled directly, but because the surface itself is curved. This idea explains why planets orbit stars and why moons orbit planets. They are not being pulled by an invisible force in the traditional sense. They are moving along curved paths in spacetime. General relativity also explains why time runs more slowly near massive objects. A clock closer to Earth's surface ticks slightly slower than a clock farther away in space. This effect is small but real and must be corrected for technologies like GPS to work accurately. General relativity made predictions that seemed unbelievable at first. It predicted that light itself would bend when passing near a massive object. This was confirmed during a solar eclipse in 1919, when starlight passing near the Sun was observed to bend exactly as Einstein had predicted. This discovery made Einstein world famous. The theory also predicted the existence of black holes, regions of spacetime where gravity is so strong that not even light can escape. For many years, black holes were considered theoretical curiosities, but today there is strong observational evidence that they exist at the centers of many galaxies. Another remarkable prediction of general relativity is gravitational waves. These are ripples in spacetime caused by violent cosmic events, such as the collision of massive stars. Einstein predicted them in 1916, but they were not directly detected until 2015, a century later. Their discovery confirmed yet another aspect of his theory and opened a new way of observing the universe. Together, special and general relativity transformed our understanding of reality. They showed that space and time are not rigid, separate entities, but part of a dynamic, interconnected structure that responds to motion and mass. Time can slow down, space can bend, and energy and mass can transform into each other. While these effects are usually too small to notice in everyday life, they dominate the behavior of the universe on very large scales and at very high speeds. In simple terms, special relativity teaches us that motion changes time and space, while general relativity teaches us that mass and energy shape time and space. Both theories reveal a universe far more flexible and strange than common sense suggests. Yet despite their strange implications, they have been confirmed again and again by experiments and observations. Einstein's relativity did not just refine physics, it reshaped how humanity understands the universe and our place within it. The equation E equals mc2 is one of the most famous formulas ever written, not because it is complicated, but because of how deeply it changed our understanding of reality. In just 3 symbols, Albert Einstein revealed a hidden truth about the universe. Mass and energy are not separate things, but 2 forms of the same essence. This simple idea transformed physics, reshaped technology, and altered how humanity understands matter, stars, and even existence itself. Before Einstein, mass and energy were treated as completely different concepts. Mass was seen as the amount of matter an object contained, something solid and permanent. Energy, on the other hand, was thought of as the ability to do work, motion, heat, light, or force. Classical physics treated them as unrelated quantities governed by different laws. Einstein's equation shattered this division. It showed that mass is energy in a concentrated form, and that energy can become mass. In the equation E equals mc2, each symbol carries profound meaning. E stands for energy, m stands for mass, and c represents the speed of light in a vacuum. The speed of light is an enormous number, about 300 kilometers per second. When squared, c2 becomes unimaginably large. This means that even a tiny amount of mass corresponds to an immense amount of energy. Matter is not just solid stuff, it is frozen energy. This insight came directly from Einstein's theory of special relativity. As Einstein explored how motion affects space and time, he realized that the traditional laws of mechanics were incomplete. Through careful reasoning, he discovered that when an object emits energy, it must lose mass, even if the change is too small to detect in everyday situations. Mass and energy must therefore be interchangeable. This was a radical conclusion, contradicting centuries of scientific belief. At first, the equation seemed purely theoretical. No one in 1905 could imagine practical ways to convert mass into energy. The changes in mass involved in chemical reactions, such as burning fuel, are so small that they are nearly impossible to measure. Yet nature itself was already demonstrating the equation on a massive scale. The stars, including our Sun, shine because mass is being converted into energy through nuclear fusion. In the core of the Sun, hydrogen nuclei combine to form helium, and a small amount of mass disappears in the process. That lost mass reappears as energy, radiating outward as heat and light. Every sunrise is a silent confirmation of E equals mc2. The equation also explains why nuclear reactions release vastly more energy than chemical reactions. In chemical reactions, atoms rearrange their electrons, releasing only a tiny fraction of the energy stored in matter. In nuclear reactions, the structure of the atomic nucleus itself changes, releasing energy directly from mass. This is why nuclear power plants can generate enormous amounts of electricity from small amounts of fuel, and why nuclear weapons release such devastating energy. Although Einstein did not invent nuclear weapons, his equation made their possibility scientifically understandable. Beyond its technological consequences, E equals mc2 forced scientists to rethink the nature of matter. At the deepest level, matter is not solid or permanent. It is a form of energy held together by physical laws. This realization led to major developments in particle physics, where particles can be created from energy and annihilated back into energy. In high-energy experiments, such as those conducted in particle accelerators, energy is routinely converted into new particles with mass, perfectly obeying Einstein's equation. The equation also changed how scientists understand the early universe. According to modern cosmology, the universe began in an extremely hot, dense state where energy dominated. As the universe cooled, energy transformed into particles, giving rise to matter. In this sense, everything we see today, galaxies, stars, planets, and people, exists because energy once became mass. E equals mc2 provides the bridge between the birth of the universe and the matter-filled cosmos we inhabit. What makes the equation especially powerful is its universality. It applies everywhere, at all times, without exception. It does not depend on specific materials, forces, or conditions. Whether in the heart of a star, the core of an atom, or the vast emptiness of space, the relationship between mass and energy remains the same. This universality is one of the reasons the equation is considered a fundamental truth of nature. Despite its fame, E equals mc2 is often misunderstood. It does not mean that mass constantly turns into energy in everyday life in dramatic ways. Instead, it tells us that mass has energy, even when it appears to be at rest. This rest energy is always present. Most of the time, it remains locked inside matter, inaccessible under normal conditions. Only under extreme circumstances, such as nuclear reactions or particle collisions, does this energy become visible. Einstein himself viewed the equation as a natural consequence of deeper principles, not as a standalone discovery. He was more interested in understanding the laws of nature than in the practical uses of his ideas. Later in life, he expressed concern about how mass-energy equivalence was applied in warfare. This highlights an important truth. Scientific knowledge itself is neutral, but how humanity chooses to use it carries moral responsibility. The cultural impact of E equals mc2 extends far beyond physics. It became a symbol of human intelligence and the power of simple ideas to unlock deep truths. Few equations have entered popular culture, but this one did because it represents a turning point in how humans understand reality. It reminds us that the universe is far stranger and more interconnected than it appears. In the end, E equals mc2 changed reality not by altering the universe, but by revealing what the universe truly is. It showed that matter and energy are two expressions of the same fundamental substance, united by the speed of light. From the glow of the sun to the origins of the cosmos, this equation connects the smallest particles to the largest structures. With one elegant insight, Einstein transformed our understanding of existence, proving that even the simplest symbols can carry the weight of the universe. Einstein's role in the birth of quantum theory is one of the most fascinating paradoxes in the history of science. He was both a founder of quantum ideas and one of their strongest critics. While quantum mechanics is often associated with names like Planck, Bohr, Heisenberg, and Schrödinger, it was Albert Einstein who provided some of its most crucial early insights. Without his contributions, quantum theory might not have taken shape in the way it did. At the same time, Einstein never fully accepted the philosophical implications of the theory he helped create. At the dawn of the 20th century, physics was in crisis. Classical theories worked well for large objects and slow speeds, but they failed when applied to atoms, radiation, and energy exchange. In 1900, Max Planck made the first step toward quantum theory by proposing that energy is emitted in discrete packets, or quanta, rather than continuously. Planck himself viewed this as a mathematical trick, not a statement about physical reality. It was Einstein who took the idea seriously and pushed it much further. In 1905, Einstein published a paper that directly challenged the classical wave theory of light. At the time, light was widely understood as a wave phenomenon. supported by experiments such as interference and diffraction. However, certain observations, especially the photoelectric effect, could not be explained by wave theory alone. When light shone on a metal surface, electrons were ejected only if the light had a minimum frequency, regardless of its brightness. Classical physics predicted that increasing intensity should increase energy transfer, but experiments showed otherwise. Einstein solved this mystery by proposing a bold idea. Light itself is made of discrete packets of energy, later called photons. Each photon carries energy proportional to its frequency. If the photon's energy is too low, no electrons are ejected, no matter how intense the light is. This explanation perfectly matched experimental results. With this single insight, Einstein extended Planck's quantum idea from energy emission to the very nature of light. This was a foundational moment in quantum theory. For this work, not relativity, Einstein later received the Nobel Prize in Physics. Einstein's work on the photoelectric effect did more than solve one problem. It revealed that nature behaves in a fundamentally discontinuous way at small scales. Energy was not infinitely divisible, as classical physics assumed. This realization forced scientists to rethink the behavior of light and matter at the atomic level. It also laid the groundwork for technologies such as solar cells, digital cameras, and light sensors, all of which depend on quantum principles. Einstein continued to contribute to quantum theory in the years that followed. In 1907, he applied quantum ideas to explain the heat capacity of solids. Classical physics predicted that solids should store more heat than they actually do at low temperatures. Einstein introduced a quantum model of atomic vibrations, showing that energy exchange inside solids is quantized. This work further confirmed that quantum behavior was not limited to radiation, but was a general feature of matter. In 1917, Einstein made another groundbreaking contribution by studying how atoms interact with light. He introduced the concepts of spontaneous emission, absorption, and stimulated emission. Stimulated emission occurs when an incoming photon causes an excited atom to emit another photon with the same energy and direction. This idea was far ahead of its time, and later became the theoretical foundation of lasers. Once again, Einstein was pushing quantum theory forward by revealing hidden mechanisms of the microscopic world. Despite these contributions, Einstein grew increasingly uncomfortable with the direction quantum theory took in the 1920s. As physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed quantum mechanics into a full mathematical framework, the theory became more abstract and probabilistic. According to the emerging interpretation, quantum theory did not predict exact outcomes, only probabilities. The behavior of particles could not be determined precisely, only statistically. Einstein strongly objected to this idea. He believed that the universe should be governed by precise laws, even if those laws were not yet fully known. His famous remark, "God does not play dice," reflected his discomfort with the notion that chance lies at the heart of physical reality. Einstein did not deny the accuracy of quantum mechanics. He questioned whether it was a complete description of nature. This disagreement led to some of the most famous debates in the history of science, particularly between Einstein and Bohr. Einstein proposed thought experiments designed to show that quantum mechanics contained contradictions or violated common sense ideas about reality. Bohr responded by showing that these objections actually revealed misunderstandings about measurement and observation at the quantum level. These debates sharpened the theory and forced physicists to think more deeply about its meaning. One of Einstein's most important critiques came in 1935 with the Einstein-Podolsky-Rosen argument, often called the EPR paradox. Einstein and his collaborators argued that quantum mechanics allowed for strange connections between distant particles, where measuring one particle instantly affected the other, no matter how far apart they were. Einstein referred to this as spooky action at a distance, and believed it indicated that quantum theory was incomplete. Ironically, this critique later became one of quantum theory's greatest strengths. Experiments conducted decades later confirmed the phenomenon now known as quantum entanglement. Today, entanglement is a central concept in quantum physics and is used in emerging technologies such as quantum computing and quantum communication. Once again, Einstein's objections helped uncover deeper truths, even when they went against his own philosophical preferences. Einstein's role in the birth of quantum theory was therefore both creative and critical. He helped launch the quantum revolution by treating quanta as real physical entities and applying them to light, matter, and atomic processes. At the same time, his relentless questioning exposed the theory's conceptual challenges and pushed physicists to refine their understanding. In the end, Einstein was not wrong to demand clarity and realism. His skepticism ensured that quantum mechanics was tested, debated, and strengthened. Although he never fully embraced its probabilistic nature, his contributions were essential to its creation and success. Quantum theory was born not only from bold new ideas, but also from deep intellectual struggle, and Einstein stood at the center of both. Albert Einstein's life was not only a story of brilliant ideas, but also a journey through scientific resistance, sudden global fame, and deep moral responsibility. His experiences in these areas reveal the human side of science, the struggles that come with challenging established beliefs, the unexpected consequences of recognition, and the ethical questions that arise when knowledge gains immense power. When Einstein first introduced his revolutionary ideas, they were met with strong scientific resistance. At the beginning of the 20th century, physics was built on the solid foundations laid by Isaac Newton. Space and time were considered absolute, light was understood mainly as a wave, and gravity was seen as a force acting at a distance. Einstein's theories challenged all of these assumptions. Special relativity questioned absolute time and space, while general relativity redefined gravity itself. Such ideas did not merely extend existing theories, they replaced them. As a result, many scientists found them difficult to accept. Resistance did not come only from misunderstanding, but also from the natural conservatism of science. Established scientists had built their careers on classical physics, and Einstein's work implied that some of their fundamental assumptions were incomplete. His unconventional background made acceptance even harder. He was not a respected professor at a major university when he published his early work, but a patent clerk working largely in isolation. To many, it seemed unlikely that such a figure could overturn centuries of scientific thought. Einstein's ideas were also mathematically challenging and conceptually strange. Time slowing down, space bending, and mass turning into energy contradicted everyday experience. Even brilliant physicists struggled to grasp these concepts at first. It took years of experimental confirmation, such as the bending of light during a solar eclipse in 1919, for Einstein's theories to gain widespread acceptance. That single observation transformed scientific skepticism into admiration almost overnight. With acceptance came extraordinary fame. After the 1919 eclipse confirmed general relativity, Einstein became a global celebrity. Newspapers around the world portrayed him as a genius who had rewritten the laws of the universe. His face became recognizable even to people with no interest in science. This level of fame was unprecedented for a scientist. Einstein was suddenly invited to give lectures, attend ceremonies, and comment on matters far beyond physics. Einstein had a complicated relationship with fame. On one hand, he understood that public attention could help promote science and rational thinking. On the other hand, he disliked the loss of privacy and the simplification of his work into slogans and myths. He was often portrayed as a mysterious genius with supernatural intelligence, a stereotype he himself rejected. Einstein believed that his achievements were the result of persistence, curiosity, and imagination, not some magical gift. Fame also gave Einstein a powerful public voice, and he chose to use it. Living through 2 world wars, he became deeply concerned with issues of peace, nationalism, and human rights. As a pacifist by conviction, he spoke out against war and militarism, especially after witnessing the devastation of World War I. He believed that science should serve humanity, not destroy it. However, Einstein's sense of moral responsibility became especially complex during the rise of nuclear physics. His equation, E equals mc2, showed that enormous energy was stored in matter. Although Einstein did not work directly on nuclear weapons, his ideas helped make their development scientifically possible. When he learned that Nazi Germany might be attempting to build an atomic bomb, he faced a profound ethical dilemma. In 1939, he signed a letter warning the United States government of this possibility, encouraging research into nuclear energy. Later, when atomic bombs were used in warfare, Einstein felt deep regret. He described the letter as the greatest mistake of his life, even though his intention had been to prevent a greater danger. This moment highlights the burden of moral responsibility that comes with scientific knowledge. Einstein understood that once ideas are released into the world, their consequences can go far beyond the scientist's control. After the war, Einstein became an outspoken advocate for nuclear disarmament and global cooperation. He argued that humanity's technological power had outgrown its moral wisdom. Science had given humans the ability to destroy themselves, and only ethical responsibility and international understanding could prevent catastrophe. He supported movements for world peace and urged scientists to consider the social impact of their work. Einstein also faced political resistance, especially later in life. His outspoken views on peace, civil rights, and internationalism made him a controversial figure. During times of political tension, some accused him of being unpatriotic or naive. Despite this, Einstein remained committed to speaking his conscience. He believed that intellectuals had a duty not only to seek truth, but also to defend human values. What makes Einstein's story so powerful is that he did not separate science from humanity. He understood that scientific progress is not just about equations and experiments, but about how knowledge shapes society. His life shows that challenging accepted ideas often brings resistance, that fame can be both a tool and a burden, and that great knowledge carries great responsibility. In the end, Einstein's legacy is not only his scientific genius, but his moral example. He demonstrated courage in the face of skepticism, humility in the face of fame, and conscience in the face of power. His life reminds us that the true measure of scientific achievement is not only how much we understand the universe, but how wisely we choose to use that understanding for the future of humanity. Albert Einstein's work has had a lasting impact on modern science and technology that reaches far beyond theoretical physics. His ideas reshaped the foundations of how scientists understand nature, and they continue to influence everyday technologies that billions of people rely on. What makes Einstein's legacy extraordinary is that concepts once considered abstract or purely theoretical have become essential tools of modern life, from navigation systems to medical imaging and from energy production to our understanding of the universe itself. One of the most profound impacts of Einstein's work lies in modern physics. His theories of special and general relativity changed how scientists understand space, time, motion, and gravity. Before Einstein, space and time were treated as fixed and separate entities. After Einstein, they became dynamic and interconnected. This shift did not just refine physics, it redefined it. Modern cosmology, the study of the universe as a whole, is built directly on general relativity. Our understanding of black holes, neutron stars, gravitational waves, and the expansion of the universe all depend on Einstein's equations. Einstein's influence is also deeply embedded in modern technology. A clear example is the Global Positioning System, or GPS. GPS satellites orbit Earth at high speeds and experience weaker gravity than objects on the ground. According to Einstein's theories, time passes at slightly different rates for these satellites compared to clocks on Earth. If these relativistic effects were ignored, GPS calculations would quickly become inaccurate, leading to errors of several kilometers. By correcting for time dilation predicted by both special and general relativity, GPS systems provide precise location data used in navigation, transportation, agriculture, disaster response, and everyday smartphone apps. Another major area shaped by Einstein's work is energy technology. His equation E equals mc2 revealed that mass and energy are interchangeable. This principle is the foundation of nuclear energy. Nuclear power plants generate electricity by converting a small amount of mass into energy through controlled nuclear reactions. While the use of nuclear energy raises ethical and safety questions, the scientific principle behind it comes directly from Einstein's insight into mass-energy equivalence. The same idea also explains how the Sun and other stars produce light and heat, making life on Earth possible. Einstein's role in the development of quantum theory has had equally far-reaching technological consequences. His explanation of the photoelectric effect showed that light behaves as discrete packets of energy. This idea is essential to modern electronics. Solar panels work by using photons to release electrons in semiconductor materials, producing electric current. Digital cameras, light sensors, automatic doors, and many types of imaging devices rely on this same quantum principle. Without Einstein's contribution, much of today's electronic and optical technology would not exist in its current form. Modern medicine has also benefited from Einstein's scientific legacy. Medical imaging technologies such as PET scans rely on principles connected to mass-energy equivalence and particle physics, which developed from Einstein's ideas. Precise timing technologies, influenced by relativity, are crucial in coordinating complex medical equipment. Even laser technology, which is used in surgeries, diagnostics, and treatments, is based on quantum concepts that Einstein helped establish through his work on stimulated emission. Einstein's impact extends beyond specific inventions to the scientific mindset itself. He demonstrated the power of questioning fundamental assumptions. Rather than accepting established ideas, he asked simple but deep questions about how the universe works. This approach has become a model for scientific innovation. Modern research in fields such as theoretical physics, astrophysics, and even artificial intelligence often follows Einstein's example. Challenge assumptions, simplify problems, and rely on imagination guided by logic. In space science and exploration, Einstein's influence is unmistakable. Space agencies rely on relativistic physics to plan satellite orbits, deep space missions, and communication systems. Observations of distant galaxies, gravitational lensing, and cosmic background radiation are all interpreted using Einstein's theories. The recent detection of gravitational waves confirmed predictions made by general relativity a century earlier and opened an entirely new way of studying the universe. These discoveries are not just scientific achievements. They shape humanity's understanding of its place in the cosmos. Einstein's legacy also includes his influence on education and scientific culture. He showed that creativity is as important as calculation, and that imagination plays a key role in discovery. This perspective has inspired generations of scientists, engineers, and thinkers. His life story, marked by early struggles, independent thinking, and persistence, challenges the idea that innovation only comes from traditional paths. As a result, Einstein became a symbol of intellectual freedom and curiosity. Beyond science and technology, Einstein's impact reaches into society and ethics. He was one of the first scientists to publicly grapple with the moral responsibilities that come with powerful knowledge. His reflections on nuclear weapons, peace, and global cooperation remain relevant today as humanity faces challenges such as climate change, artificial intelligence, and advanced biotechnology. Einstein's example reminds scientists and engineers that their work does not exist in isolation from human values. In the modern world, Einstein's ideas continue to guide research at the frontiers of knowledge. Efforts to unify gravity with quantum mechanics, explore dark matter and dark energy, and understand the origins of the universe all depend on the foundations he laid. Even when scientists move beyond Einstein's theories, they do so by building on them, testing their limits, and extending their insights. In the end, the lasting impact of Einstein on modern science and technology lies not only in specific equations or inventions, but in a transformed view of reality. He revealed a universe where space and time are flexible, where matter and energy are interchangeable, and where unseen principles shape everything we observe. His ideas power technologies we use every day and inspire scientific exploration that continues to reshape the future. Einstein did not just change science for his own time. He changed the trajectory of human understanding for generations to come.